Exercise 11. In this one, this equation is given. On the left hand side we have the complex number a plus ib, and on the right hand side we have this complex number x plus I whole square divided by 2x square plus 1. It's of course understood that a and b are real numbers and x is also a real number, and we have to prove this, that the sum of the squares of a and b equals this. Here however we do not see any I. Now before we go to the proof, let us note one thing, that this denominator 2x square plus 1 is a real number. It's a complex number of course, but in particular it's a real number. So we of course start the proof with what is given, that is this equation, and then we take the square of the absolute value on both sides, square of modulus. So the left hand side becomes a square plus b square. Straight away we are getting what we want on the left hand side. Why do we have simply a square plus b square and not square root? That is because we are taking not just modulus but its square. Well, what will happen to this side? First, the modulus will get distributed over the ratio. Mod square of the numerator divided by mod square of the denominator. And then we do not have to touch the left hand side. You can continue writing it like this, or you can start with this itself and then you write equations, a chain of equalities. But anyway, we have started like this. So we keep writing a square plus b square. Okay. Now this x plus I whole square, in its place I have written x plus I times x plus I. That mod square, it remains. What is happening to the denominator? Just now I have said that 2x square plus 1 is a real number, and actually it's a positive real number. Even when x is negative, because there is square, you are going to get positive value. So its modulus will actually be equal to itself, and already there is square, so 2x square plus 1 whole square. So that way you go back and see the statement of the problem. This is what you need finally as your denominator. So all we now have to do is to manipulate the numerator, and here next what do? We distribute this mod square over the product, which we can do because modulus of z1 z2 is equal to mod z1 times mod z2, and the same thing also happens when you have square over modulus. So that way we have this, and now you can calculate this. What is this? The ordinary modulus of x plus I will be square root of real part square, that means x square, plus imaginary part square. Imaginary part is 1, so root x square plus 1, but there is a square, so only x square plus 1 times x square plus 1. So that's how you have your thing. Next, number 12. Here two complex numbers are given, z1 and z2. z1 is 2 minus I and z2 is minus 2 plus I, and it has two parts. In the first part we have to calculate the real part of z1 z2 divided by the conjugate of z1, and in the second part we have to calculate the imaginary part of 1 divided by z1 times its conjugate. So part 1. Before we go to the real part of the number, let us write the number itself and manipulate it. So z1 z2 is this 2 minus I times minus 2 plus I divided by the conjugate of z1, that is 2 plus I. So you can go through the calculation yourself. You see that this will become minus 3 plus 4I, and then of course in the next step we make the denominator real by multiplying and dividing by the conjugate of the denominator, which is 2 minus I. And that gets us minus 2 plus 11I divided by 5. So which when you express in the standard form, you get this minus 2 over 5 plus 11 divided by 5 times I. So that means the real part is minus 2 divided by 5. The second part is really nice. Here we have to calculate the imaginary part of this number. No. So we first concentrate on this product z1 bar, which we know is the square will be outside, sorry. The square of the absolute value of z1. Now that is a real number. So that means actually a positive real number. In general it will be non-negative. That means it can be 0 also, but in this case for our specific number z1 it is positive. So its reciprocal is also a real number. That means its imaginary part is equal to 0. So that's why it is 0. Next, 13. Here this complex number is given 1 plus 2y divided by 1 minus 3i. We have to find its modulus and arguments. Because we have already gone through similar problems before, so instead of a detailed solution, let me give you the hints. First, you have to simplify the complex number and turn it into the standard form. So when you go through the necessary steps, this is what you finally get, minus 1 over 2 plus 1 over 2 times I. And you know what the necessary steps are. Mainly you just have to turn the denominator into a real number. And for that, what should you do? You have to multiply and divide by the conjugate of the denominator. That is, multiply and divide by 1 plus 3i. And then you do the calculations and this is what you will get. So from this, how do you find the modulus? Modulus is square root of real part square plus imaginary part square. And when you do the calculation, you get 1 divided by square root of 2. And then, if theta is an argument of this complex number, then modulus times cos theta is equal to real part, that is minus 1 divided by 2, and modulus times sin theta is imaginary part, which is 1 divided by 2. And in place of modulus, you put this and then you do the cancellation, which happens, and this is what you finally are going to get, from which you know how to get to this conclusion. You note one thing, that cos theta is negative and sin theta is positive. Cos theta is negative and sin theta is positive. That means the terminal ray of your angle theta, when it is put in standard position, should lie in the second quadrant. However, if you ignore the sign for a moment, then what is the theta value that gives you cos theta and sin theta both equal to 1 divided by root 2, pi divided by 4. And then you adjust things. I won't say anything more than that. We have done this many times. So that's how you get this value of theta, which is one argument, and all the arguments are obtained by adding multiples, integer multiples of 2 pi to this angle. Here you have to mention that n is an integer. Incidentally, this is actually the principal argument, because this is greater than minus pi and less than or equal to pi. Next, 14. It is given that x minus iy times 3 plus 5i is equal to the conjugate of this complex number minus 6 minus 24i, which means that this is equal to minus 6 plus 24i. From that, we have to find the real numbers x and y. So here also I will give you just the hints, and the calculation part will be left to you. So it's given that this product is the conjugate of minus 6 minus 24i. That means this is equal to minus 6 plus 24i. So dividing both sides by 3 plus 5i, you get this. And then this is what you have to do. This ellipsis indicates the missing steps. You know what to do. You turn the denominator into a real number by multiplying and dividing by 3 minus 5i, the conjugate of 3 plus 5i. And then when you finish your calculation, this is what you get, 3 plus 3i. So x is equal to 3 and minus y is also equal to 3. That means y is equal to minus 3. Next, 15. Here we have to find the modulus of this complex number. 1 plus I divided by 1 minus I minus 1 minus I divided by 1 plus I. So for this one at least, let's see the entire solution. The complex number looks very complicated at first, but actually it's very easy. So we straight away consider its modulus. And then of course we start turning the denominators into real numbers. So here the denominator is 1 minus I, so we multiply and divide by its conjugate 1 plus I. So that's how we have 1 plus I square in the numerator. Similarly, here we multiply and divide by 1 minus I, the conjugate of 1 plus I, which is the denominator here. Now, what are these squares? If you expand these squares, you get 1 square plus I square, which is 0 because I square is minus 1, plus 2 times 1 times I, that means 2I. Similarly, here you will have minus 2I. And what about the denominators, both of which are 1 minus I times 1 plus I. 1 square plus 1 square, that is 2. So after you simplify this, you get 2I because first the 2's get cancelled and then I minus minus I, which is 2I. So the modulus of this is just 2, of course. And that's it. That is the answer. And let me just end the video here itself. There are a few other exercises that we will hopefully complete in the next video next week. So see you next week with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.